Hi, I'm Matt, and in this video we're going to talk how to find the first derivative using implicit differentiation. So before we could talk about implicit differentiation, we first should talk about what the difference between an explicit and an implicit equation is. So in the following discussion, we're going to assume x to be the independent variable, the thing we plug in, and y to be the dependent variable, what we expect to get out. So in an explicit equation, we have that the dependent variable is expressed solely in terms of the independent variable, such as essentially the form y equals f of x. We have a y on the left side, and then we have something containing an x on the right side. And in particular, there's no y's on the right side of the equation. So an example of this would be y equals 7x plus 5 minus ln of x. Again, you see we only have a y on the left side of the equation. In an implicit equation, we get a relation, so we have both an x and a y, but one variable is not necessarily expressed in terms of the other. So for example, xy plus 2x minus 8y equals 6. We see that on one side of the equation, we have both x's and y's, and in this particular case, what we notice is we can't even really solve for one variable in terms of the other, or at least not easily. So now let's talk about explicit differentiation. This is just a fancy name for what we standardly do when we take derivatives. So for example, when we have y of x is equal to 6x squared, and we take the derivative using power rule and get 12x. That's explicit differentiation. But there's some stuff that we kind of just sweep under the rug when we do this that we need to talk about to discuss implicit differentiation. In particular, let's look at the left-hand side, where we differentiate y of x with respect to x. Typically, we would just replace y with dy dx. But what exactly is going on there? So we're actually using the chain rule since it's a composition of functions. We have y being composed of x, where y is our outside function, and when we differentiate it, we get dy dx. And x is our inside function, and when we differentiate with respect to x, what we're actually getting is dx over dx, which is equivalent to 1. So when we multiply this as we would in the chain rule, because we get the derivative of the outside times the derivative of the inside, we get dy dx times 1, or dy dx. So that's how we get the dy dx on the left side, and you'll see why this is important shortly. And then on the right side, this is what we standardly do with power rule, where we multiply the 2 by the 6 to get 12, and then we're left with an x at the end. So now we see that when y is involved in our derivative, we must include a dy dx afterwards. So now this leads us into implicit differentiation. When an equation is defined implicitly, we're going to have to use implicit differentiation to find the derivative. And to do this, the left and the right-hand side are both differentiated regardless of if they contain an x, y, if they just contain constants. Doesn't matter, we take the derivative of both sides using the standard rules for explicit derivatives, our standard power rule, product rule, etc. But anytime we have something with a y in it, we'll notice that a dy dx appears in the term's derivative. And we'll see this in the examples later. Other than that, we could just differentiate with the standard derivative rules. And as a final note, that when we take a derivative using implicit differentiation, it's very common for us to get a derivative that depends on both x and y. That's fine. There's nothing wrong with that. So now, to give some more concrete steps on how we're going to do this, we're going to take the derivative of the left side of the equation, and again, remember to be mindful to include a dy dx after anything with a y. We're going to take the derivative on the right side of the equation. I didn't write it, but again, being mindful of where we need a dy dx. And then we're going to rearrange the terms so that we have all terms with a dy dx on one side of our equation, and then on the other side of the equation, we should only have terms without a dy dx. And then we'll finish solving for dy dx in terms of x and y. So let's try an example of this. So we see that we have x squared plus y squared is equal to 9. So the first thing I'm going to do is just write our equation. Again, x squared plus y squared equals 9. And now, as the steps say, we're going to first start by differentiating the left-hand side. So when we differentiate the first term, x squared, this we know just to be 2x from power rule. Similarly, when we differentiate y squared, we're going to multiply the 2 in front as we would with power rule and get 2y. However, since there's a y here, we know that we also need to include a dy dx afterwards. So now we're done differentiating the left-hand side, and we need to differentiate the right-hand side. 9 is just a constant, so when we differentiate it, we're going to get 0. Now that we've differentiated both sides, we're going to want to rearrange the terms so that we have only terms with a dy dx on one side, and then terms without on the other side. So to do that, I'm going to subtract 2x from both sides, and this will give us that 2y dy dx is going to be equal to negative 2x. And now here we want to get dy dx by itself. That's just a matter of algebra for isolating the dy dx. So I'm going to divide by 2y on both sides, and I'm going to get dy dx is equal to, notice that the 2's cancel out, negative x over y. And this here is our final answer. So we see that using implicit differentiation, we get the derivative dy dx is equal to negative x over y. Now let's try another example. Here we're given sine of x plus 3y squared is equal to x squared. So again, I'm going to just write our equation, sine of x plus 3y squared equals x squared. And then we're going to start by differentiating the left-hand side. The derivative of sine of x is going to be cosine x. And then the derivative of 3y squared, again, this is just power rule, is going to be 2 times 3 is 6y. It's going to be y to the first power because 2 minus 1 is 1. But then since we differentiated something with a y, we need a dy dx. So that's it for the left-hand side. And then for the right-hand side, we just need to differentiate x squared, which we know that derivative using power rule is 2x. So now I see that just our 6y dy dx term is the only term with a dy dx. So again, we want to isolate that dy dx. So to start, I'm going to subtract a cosine x from both sides. And that will give me 6y dy dx is equal to 2x minus cosine x. And now to isolate dy dx, we're going to divide both sides by 6y. And that gives us that our final answer using implicit differentiation gives us that dy dx is going to be equal to 2x minus cosine x all over 6y. And that would be our answer. So now, for our final example, we have x squared y plus 5x equals y squared. So again, I'm just going to start by rewriting our equation. And now we'll start by differentiating the left-hand side. However, we do notice something when we differentiate the left-hand side. This here, x squared y, is the product of two terms, so we need to use product rule. So remember that product rule says d dx of a function u times a function v is going to be equal to du dx v plus u times dv dx. So here we're going to again set u to be the first term, so u will be x squared, and then therefore du dx will be 2x. And similarly, v will be our second term, our y. So when we take dv dx, that will just be 1. However, remember we differentiate the y here, so that would be 1 times dy dx. So we get that dv dx is actually just equal to dy dx. Therefore, we get that the derivative of this first term from the product rule will be, again, du dx times v. So that will be 2xy. And then plus u dv dx. So x squared dy dx. And now we have our second term, our 5x. The derivative of that will just be 5. And then on our right, and now we need to go to step 2 and differentiate the right-hand side of our equation. the derivative of y squared will be 2y, but since we differentiated when there was a y, we need a dy dx. Now finally, we just need to isolate the dy dx. So to do that, I'm going to move the x squared dy dx to the right-hand side of the equation. And when I do so, I get 2xy plus 5 is going to be equal to 2y minus x squared, and then I could put that in parentheses and factor out the dy dx. So now finally, we see that on the left-hand side, we have no dy dx. On the right side, we have something multiplied by dy dx. So to isolate dy dx, we could just divide by 2y minus x squared. And doing so gives us that our derivative, dy dx, implicitly differentiated, we find that the derivative is 2xy plus 5 over 2y minus x squared. And this here is our final answer for the implicit derivative. Now that we've worked through some examples, here are some problems for you to try on your own. The answer to these problems will appear in 5 seconds. Okay, for the first question, you should have gotten dy dx is equal to x squared over y squared. This one was kind of similar to our first example. For problem 2, you should have gotten that dy dx was cosine x divided by sine of y. If you didn't get this, remember that when we differentiate cosine y, we'll get negative sine y times dy dx. For problem 3, you should have gotten dy dx is equal to 12y divided by y minus 1. Again, be careful when you differentiate ln of y. You should have gotten 1 over y times dy dx. And lastly, for problem 4, you should have gotten y minus y squared divided by x plus y squared, where here you likely used quotient rule for the left-hand side. If you didn't get these, feel free to leave any comments you have below. And also, if you didn't get this exact form, definitely check either by graphing them or using the internet to see if you got something equivalent. Because when we do implicit differentiation, sometimes we get answers that look a little different but are actually the same thing. With that, thank you for watching. Have a good day.